This is the last example in 4.7, the precipitation reaction section. We're determining how many grams of silver chloride, our precipitate, can be prepared by reacting 100 mils of 0.2 molar silver nitrate with 100 mils of 0.15 molar calcium chloride. The first thing we want to do is to write a balanced equation between our two reactants, the silver nitrate and the calcium chloride. And because those two are going to make silver chloride and calcium nitrate, our balanced equation will look something like this. Silver and calcium will exchange ions, and we will need to balance our equation with the coefficients of 2 for each of the compounds containing silver. Our second step in a solution stoichiometry problem is to find the moles of our reactants. If we can only find it for one, we should do that, but in this case we can find it for both, because we have a volume and a concentration for both reactants. To get moles, we will need to convert those milliliters into liters. So we'll take the 0.1 liters of silver nitrate and multiply it by the concentration, remembering that big M also represents moles over liters. That cancels out our liters and leaves us with 0.020 moles of silver nitrate. We can do the same type of calculation to get the moles of the calcium chloride. And when we do that, we see that we will have 0.015 moles of calcium chloride. Because at this point we do not know which reactant is limiting, we would need to figure out which reactant makes a smaller amount of silver chloride by performing a stoichiometry calculation, starting with the moles of each reactant. So if we start with 0.020 moles of silver nitrate, and we want to cancel out the moles of silver nitrate, we would need to have a 2 in front because of the coefficient in the balanced equation. And to get to grams of silver chloride, we would calculate its molar mass and multiply it as well by 2. And that would tell us that we are going to make 2.9 grams of silver chloride from this 0.2020 moles of silver nitrate. We would do the same thing with calcium chloride. And if you notice, the only thing that has really changed in your setup is what you've divided by. The numerator of your conversion factor has not changed. And so if you recognize from the beginning that because silver nitrate, its quantity in moles is going to decrease to 0.010, you may recognize that this actually is going to be the amount of product that can be made, because silver nitrate would be your limiting reactant. That's just a shortcut you can use, and if you would like more clarification on that, just ask me in class. When we do the math through for the second half, we do indeed see that calcium chloride can make more silver chloride than the silver nitrate can, which means the 2.9 grams of silver chloride is the most product we can make. Now, we know from this problem how many moles of the two reactants we had, and we also know what the new volume is, because when you combine 100 mils of both reactant solutions together, your new volume would be approximately 200 mils. Those are going to be important things for us to keep in mind with the second part of the problem, and that is determining the concentration of each ion in solution once the precipitation reaction is completed. I gave you a series of steps for these as well back at the beginning of 4.7, and the first thing it asks you to do is to identify the ions that you have in your mixture, which are basically the two ions making up the silver nitrate compound, so silver and nitrate, as well as the two ions making up the second compound, calcium and chlorine. The ion that was used to determine your theoretical yield, the amount of product you can make in your previous reaction, is no longer present in the mixture since it was used completely. So if we go back to our previous problem, we determined that silver nitrate was our limiting reactant because that made the smaller amount of product, 2.9 grams. With that in mind, all of the silver was consumed to make that silver chloride product. So the actual concentration of silver in our reaction mixture would be 0. Because again, all of the silver was used to make the silver chloride. Just as a reminder, I talked about these before I got to this slide. These are the amounts of moles you have of both reactants, as well as the total volume you have of your mixture. And that just came from the first part of the problem. We're going to take a look at the spectator ions now. And because the spectator ions themselves are not changed during this reaction, their amount in moles does not change, but their volume does. In calcium chloride, we have 0.015 moles, and because there is one calcium ion in calcium chloride, we have that many moles of calcium ions in our solution. Because our new volume is 200 mils, we would take that 0.015 moles and divide it by 0.2000 liters, and that would give us a concentration that's approximately half of what we had to begin with, 0.075 molar. We would do the same thing for the nitrate, taking the moles of the nitrate ions, which are in a 1-to-1 ratio with the compound, so they would have the same number of moles as silver nitrate, divide it as well by the new volume, and we would round that to 2 sig figs, 0.10 molar. The last part's probably the trickiest, but it's using stuff that we've done before in terms of excess reactant calculations. We use some of the chlorine in calcium chloride to make the silver chloride precipitate, but we did not have to use all of it. So we need to determine how much we had to begin with, how much was consumed, and once we know what is remaining, we can divide it as well by the total volume to get its new concentration. So the chlorine ion is actually twice the concentration, or twice the amount in moles as the calcium chloride compound, because there's two chlorines in CaCl2. So we would start with 0.030 moles of calcium chloride. If you were to write a net ionic equation between silver and chlorine, you would see that you need one of each of those to make the silver chloride ion. And if you used all of the silver up, then you had to use 0.02 moles of chlorine to neutralize all of that silver. You could set that up as a stoichiometry problem where you take the 0.02 moles of silver ions and you do a 1-to-1 ratio from the balanced equation between silver and chlorine, making that precipitate. But what this all ends up telling us is that because we had two chlorines in calcium chloride, we started initially with 0.030 moles of chlorine ions. We used 0.02 moles of those chlorine ions to use up all of our silver, and that leaves us with 0.01 moles of chlorine ions in the mixture. This one was kind of nice because it was a 1-to-1 ratio. If the stoichiometric ratio is not 1-to-1, you have to account for those coefficients. So just like we did before, you would need to figure out your initial amount, complete a stoichiometry problem to determine how much was used, and then take the difference between the two. Once we know how much chlorine is produced, we can take that amount in moles and divide it by the volume to get chlorine's concentration of 0.050 mole. So that's the end of the first example that we're going to talk about. The second example is at the end of your packet, number 3, at the end of 4.7, with acid-base neutralization. So this last example is involving nitric acid and calcium hydroxide. So we're looking at a neutralization reaction. And when nitric acid and calcium hydroxide combine, you're going to make water along with the salt of the remaining ions, calcium nitrate. And to balance this equation, you're going to need 2 moles of nitric acid for every 2 moles of water. Again, the next step we want to do is to figure out the moles of our reactants. In this case, we can find it for both. So we would take our volume and our molarity to get moles for nitric acid and as well for calcium hydroxide. If we look right now, it appears that calcium hydroxide is going to be our limiting reactant because it is the smaller quantity in moles. And even if we take a look at the coefficients up here, we see nitric acid has a 2. And if you take half of that molar amount, you're still going to have more moles of nitric acid than calcium hydroxide. So calcium hydroxide is most likely going to be our limiting reactant. I'm going to go ahead and do the 2 stoichiometry problems to confirm this, but if you see that, you can get away with just doing one of them. And if you need to pause, if you're still writing information down from above, I would do so now, because I'm getting ready to work those stoichiometry problems. So I'm going to start with my nitric acid, and I'm going to figure out from that amount of nitric acid how much water I can make. You typically can't measure moles, but you can measure grams. So I'm going to find out the grams of water I could make in this reaction. And so for every 2 moles of nitric acid, according to my balanced equation, I would need 2 moles of water, and since I want grams, that would be 2 times 18.02 grams of water. The moles of nitric acid cancel out. I multiply across, and I get, divide by 2, 0.209 grams of water. So in theory, the amount of water made from the calcium hydroxide should be smaller. We're starting with 0.00426 moles of calcium hydroxide. Calcium hydroxide's coefficient is 1, so for every 1 mole of calcium hydroxide that is used, I would also make 2 moles of water, and that would give me 0.155 grams of water. So calcium hydroxide is indeed my limiting reactant, and I have figured out from the amount of my limiting reactant the desired product or information I'm looking for in my problem. So 0.155 grams is the amount of water that could be produced with the amounts of reactants in this reaction. We're also going to figure out from this information which ion, hydrogen or hydroxide, we have left over and what the concentration is of that ion. We have the moles of our nitric acid as well as the moles of the calcium hydroxide. And as we just talked about, keep in mind that we used up all of the hydroxide to make this water. So our excess ion is going to come from the nitric acid. But we'll see that on the next slide. So since we know that the hydroxide is at 0 because it was used up completely, hydrogen has to be our 0.116 moles of nitric acid. And because I have a 1-to-1 ratio of hydrogen to nitric acid, that gives me my initial amount of hydrogen ions I had present. All of the calcium hydroxide was consumed in this reaction, specifically towards the hydroxide ion. But because there's 2 hydroxide ions in calcium hydroxide, the moles of hydroxide consumed would be twice this. So if I take my initial amount of hydrogen, 0.0116 moles, and I subtract from that twice this amount of calcium hydroxide, again because of the 2-to-1 ratio of hydroxide to calcium hydroxide, hydrogen and hydroxide react in a 1-to-1 ratio to make water, so I have 0.0031 moles of hydrogen remaining once the reaction is complete. To get the concentration of hydrogen ions present, I would need to take the moles that I had left over, divided by the volume, which was the volume of the nitric acid and the calcium hydroxide that I started with, added together, converted to liters. So I take the 0.0031 moles, and I divide it by the 0.0614 liters to get the 0.050 molar concentration of hydrogen ions in my reaction mixture. So this should help you with the 4 problems that were on the back side of the worksheet. The first part of each of these 2 problems should help review the front side of your worksheet.